Welcome back, friends. So in the previous session we have started with the Fourier transform. Now in the Fourier transform, next thing what we have to see is convergence of Fourier transform or convergence condition of Fourier transform. What is a convergence condition? Convergence condition of Fourier transform. Okay, try to understand. So many people, they are actually confusing with the convergence condition and existence of Fourier transform. Both are not same, not at all same. So convergence condition is a different one and existence of Fourier transform is a different concept. We will see both. So first you can understand what is a convergence condition. Suppose if I take x of omega, this is the Fourier transform, and we are having this integral value minus infinity to infinity x of t e power minus j omega t dt. This is what the Fourier transform we have. So in this Fourier transform, suppose because of the integrals are from minus infinity to infinity, this is an improper integral, and this value can be infinity also. This value can be infinity also. There is a possibility this value is going to be infinity also. So I don't want x of omega to be infinity. Then we can call x of omega is convergence. So what do you mean by that? Fourier transform is converging means this x of omega or this integral value should not be infinity. So this value must be finite for all the values of omega. So if you consider different omega values, you are going to get finite values. Okay, that's what it is. So can I simply say x of omega is converging or x of omega is finite, or simply we can call x of omega is bounded? Understood? So x of omega has to be bounded, then we can say it is converging. That's what I can say. So when can we say x of omega is bounded? Suppose if I take mod x of omega, that is equal to mod integral minus infinity to infinity x of t e power minus j omega t. So if I apply modulus here, from the squared inequality it is less than or equal to, I can take this modulus inside the integral. There it is, mod x of t mod e power minus j omega t dt from squared inequality. From squared inequality we can write like this. So now you tell me, what is this modulus of e power minus j omega t? What is the magnitude of e power minus j omega t? That is going to be 1. So from this I can say mod x of omega is less than or equal to integral minus infinity to infinity mod x of t dt. So this has to be bounded. That means it has to be always less than or equal to some maximum value. This is the maximum value for it, and this should not be infinity. So it has to be less than infinity. So x of omega converges means this value should never go to infinity if this integral minus infinity to infinity mod x of t dt has to be less than infinity. That value should never go to infinity. Or simply can I say x of t must be absolutely integrable. That is, x of t must be absolutely integrable. Absolutely integrable. Absolutely integrable. So this is what we have to say, the convergence condition. What is that convergence condition? X of t must be absolutely integrable. That means absolute value of x of t must be integrable. So the integral value should be finite. It will never go to infinity. So this is the convergence condition. Okay, take it. Then once we understand the convergence condition, then we will see the existence of Fourier transform. For what kind of signals the Fourier transform is going to exist. So many people think that this is the same condition which is for Fourier transform also, existence of Fourier transform. That is not true. This condition is for convergence condition of Fourier transform. That means x of omega must be bounded. Okay, take it. Oh. So let's see. I will give you three kinds of signals, you can understand. Suppose a signal x of t is equal to r of t, which looks like this. Second signal x of t is equal to u of t, step function. Let's say this is the one whose value is equal to 1. Third signal x of t is equal to e power minus at u of t, where a is greater than 0. Then it is going to be decaying exponential, which is like this. Which is like this. Now, observe carefully about these signals. Then, which one is going to be having Fourier transform which is converges? For what kind of signal Fourier transform converges? Here, listen. If I try to find out area under this curve, definitely integral minus infinity to infinity mod x of t dt value is equal to infinity, because it is a growing, so it's a linearly growing function, and the area under this function is going to be infinity. Next, coming to this one. So if I try to find out area under this one, so you can consider it as a rectangle whose length is equal to infinity, height is equal to 1, then total area under this curve, it is also going to be infinity. Integral minus infinity to infinity mod x of t, here also going to be infinity. What about this function? If I try to find out area under this function, modulus of this integral minus infinity to infinity mod x of t dt, whose value is not equal to infinity. Whose value is not equal to infinity. So out of these three signals, this one having Fourier transform which is converges. Out of these three signals, which one? This one has having converged Fourier transform. What about other these two signals? These two signals have Fourier transform does not converge because it is not satisfying the absolutely integrable property. Now, if you observe carefully, this one is an unbounded function, this one is a bounded function, this one is a bounded function. So between these two signals, we are having one similarity, both the signals are bounded and this one is unbounded. So if I ask, for this signal, Fourier transform exists or not? Yes, Fourier transform exists. If I ask, for this signal, Fourier transform exists or not? Yes, it is also the true. Why? Because it is a bounded signal. So Fourier transform exists here also. Here, Fourier transform exists? No, Fourier transform does not exist. Does not exist. You have to understand, how can we say Fourier transform exists or not? It is not because of this convergence condition, it is because of bounded and unbounded signals. So remember, whenever the signal is bounded, for that signal Fourier transform exists. Next, if it is a unbounded signal, Fourier transform does not exist. Then what is the convergence condition? See, even though it is a bounded, Fourier transform does not converge. That means Fourier transform exists but not converging. But here, if you take, here Fourier transform exists and also converges. So let's take these three signals in a different manner. So consider this signal. Can I call this signal as a neither energy nor power signal? Yes, it is a unbounded signal. So we can name them neither energy nor power signal. What about this signal u of t, which is a power signal? Which is a power signal. Power signal. What about this signal e power minus at u of t, which is a energy signal? energy signal. Okay. Listen carefully. We are having three categories: energy signal, power signal, neither energy nor power signal. If somebody is asking, for energy signal, is Fourier transform exist? Answer is yes. Fourier transform definitely exists. Is it going to be converge? That means for all the values of omega, it is having finite values only. That means its value never go to infinity. Yes, x of omega is converging means it will never go to infinity. That means its values are always defined, not undefined like infinity. So it is called as well-defined Fourier transform. So for energy signals, the Fourier transform is existing and it is defined for all the values of omega. That's why for energy signals, we are having a Fourier transform which is called as well-defined Fourier transform. Whereas power signals, because it is a bounded signal, Fourier transform exists or not? Yes. For a bounded signal, Fourier transform exists. But is it going to converge? No. For certain values of omega, that is going to be infinity. X of omega value is going to be infinity. So can I simply say like this? Fourier transform exists, but it is limitedly defined. Why it is limitedly defined? It is not going to be converging for all the values of omega. For certain values of omega, it is going to be infinity. That means undefined. So I can say it is having Fourier transform, but it is not well defined. It is limitedly defined Fourier transform. Whereas coming to neither energy nor power signal, because it is always unbounded, so we can directly say no Fourier transform exists for neither energy nor power signals. But there are two exceptions for neither energy nor power signal, that means unbounded. One is delta t, another one is 1 by t. So except these, so for every unbounded signals, we don't get the Fourier transform. So those points I am going to write here. First one, neither energy nor power signal. So I can directly say for all unbounded signals, Fourier transform does not exist. For unbounded signals, Fourier transform does not exist. Does not exist. For unbounded signals, Fourier transform does not exist, except delta t and 1 by kt. So this is also unbounded function. In particular, we can say kt power n also 1 by kt power n. So for these signals, even though they are unbounded, we are having Fourier transform for them. Next, second case, energy signals. Energy signals. For energy signals, we are having Fourier transform and it is a well-defined Fourier transform. Well-defined Fourier transform. That is, x of omega is defined for all the values of omega. For all the values of omega. Next, third category, which is power signals. For power signals, we are having the Fourier transform, but it is limitedly defined Fourier transform. Limitedly defined Fourier transform, that is x of omega is not defined. Not defined. What do you mean by not defined? Its value is going to be infinity. Not defined for certain values of omega. For certain values of omega. For certain values of omega. Okay, so these are the things we have to remember. Take it. Then how we can calculate the Fourier transform for them, and you have to remember them also. Okay, let's say the first one, Fourier transform of x of t, which is equal to delta t. For impulse function, I told you just now, even though it is an unbounded function, still we are having the Fourier transform for it because it is an exceptional one. Okay, so x of omega I have to calculate. That is direct formula I am using, integral minus infinity to infinity x of t, that is nothing but delta t, e power minus j omega t dt. Wherever any function is multiplied with delta t, then t has to be replaced with 0. This is the multiplication property of impulse function. We already seen that. So if t is replaced with 0, then it is going to be 1. So finally integral minus infinity to infinity delta t dt, whose value is equal to 1. So remember this one direct. For impulse function, we are having Fourier transform, which is 1. Which is 1. That means if I draw this spectrum, so let's say delta t, which is x of t, where it is existing at 0, right? So delta t function which is existing at 0, 1. So this is x of t function which is equal to delta t. For this function, what is the Fourier transform x of omega? We got, which is equal to 1. So with respect to omega, it is going to be constant value. It is going to be constant value. That means its value is equal to 1 for all the frequencies. What do you mean by this? I already told you Fourier transform is going to determine the frequency content of the given signal. So what does this means? Delta t, it is having all the frequency components with equal magnitude. I hope you understood. That's what the meaning of it. So what kind of frequencies which are present in the delta t? That is nothing but 0 to infinity. That means every frequency having the same magnitude. That means it is having every frequency in the impulse function. That's why you might know LTI systems are mainly represented with impulse response. Why? What do you mean by that? For an impulse function, if you could know what is the output, which is nothing but impulse response. If you know the impulse response means, that means you know the response for all the frequencies. That's what the meaning of it, because impulse function is having all the frequencies. So if you know for all the frequencies, if any signal is given, so that signal may not have all the frequencies, that signal may have only limited number of frequencies. So for that you can easily find out the response. That's why the impulse response is very, very important, because it is having all the frequencies from 0 to infinity. So that's what the meaning of it. So it contains every frequency. Next, another one. What is the inverse Fourier transform of delta omega? Inverse Fourier transform of x of omega, which is equal to delta omega. For x of omega, we have to find out inverse Fourier transform. So what is x of t? Formula we know. X of t, which is equal to 1 by 2 pi integral minus infinity to infinity x of omega, that is delta omega e power j omega t d omega. So what do you mean by that? If any function is multiplied with delta omega, omega has to be replaced with 0. Then this part is going to be 1. So 1 by 2 pi integral minus infinity to infinity delta omega d omega. Delta omega d omega. So what is this integral value, which is going to be 1? So finally this is 1 by 2 pi. 1 by 2 pi. So this is x of t expression, not x of omega, it is x of t. That means time domain, if it is 1 by 2 pi, time domain if it is 1 by 2 pi. For this, what is the frequency domain x of omega? That is nothing but delta omega. Delta omega. That's what the meaning of it. So if time domain x of t is equal to 1 by 2 pi, then what is the Fourier transform for this? Delta omega. So if I say, if I multiply entire both sides by 2 pi, then it is going to be 1 having Fourier transform 2 pi delta omega. 2 pi delta omega. So this is the Fourier transform. Suppose let's say if x of t is this one, or better we will take x of t is equal to 1, then what is x of omega? 2 pi delta omega. 2 pi delta omega. Pi delta omega. Suppose if I want to find out x of f domain, then 2 pi omega has to be replaced with a 2 pi f. We know delta at, which is nothing but mod a delta t, which is similar to this one. So delta 2 pi f. So bring this 2 pi outside, then it is going to be 2 pi get cancelled. Finally delta f. So that means if I take x of t is equal to 1, for that what is x of f, which is equal to delta f. Delta f. So if I draw what is this function, suppose if I take spectrum x of f spectrum this time, t in time domain its value is equal to 1, that means constant. For this, what is x of f? We got x of f with respect to f. At 0 we are having impulse function. So this is what we got. What does this indicate? That means DC signal having a frequency which is nothing but 0. That's why we are having only one component which is existing at 0. That means it is having only single frequency which is nothing but 0. That's what the meaning of it. So in the frequency domain, f domain, it is more visible. What is the amplitude of this function? Which is nothing but 1. Amplitude of the function is nothing but 1. Okay, so I hope you understood. DC signal having a single frequency, that's why we are getting one impulse function at omega is equal to 0. Take this. Next, one more function. X of t is equal to e power minus at u of t, where a is greater than 0. For this function, we have to find out Fourier transform. Why they have given this condition a greater than 0? Why can't it be a less than 0? That means, let's take one example. A is equal to minus 2. I am opposing this condition. I am taking a is equal to minus 2. If a is equal to minus 2, then it is going to be, if a is equal to minus 2, then it is going to be e power 2t u of t, which is a growing exponential. For this growing exponential, we don't have any Fourier transform. Why? It is an unbounded function. I told you, for unbounded signals, Fourier transform does not exist. So that's why this condition has to be there. A greater than 0 has to be there. For this, I have to calculate Fourier transform. Because it's the energy signal, I can directly go with the formula. X of omega is equal to integral minus infinity to infinity e power minus at u of t, e power minus j omega t dt. Because of this u of t, I can take the limits from 0 to infinity. E power minus a plus j omega into t dt. So for this integration, e power minus a plus j omega t by minus a plus j omega 0 to infinity. Because of this negative sign, first I can substitute a lower limit e power 0, that is going to be 1, minus e power minus infinity, that is going to be 0. So finally 1 by a plus j omega. So you have to remember e power minus at u of t having Fourier transform 1 by a plus j omega, 1 by a plus j omega. Some more analysis on this function. Let's see. I hope this is also over. Here we got x of omega, which is 1 by a plus j omega. So for this, I want to draw the spectrum. How the spectrum may look like. So let's see. First, what is mod x of omega? So what is the modulus for this function? 1 by root a square plus omega square. So this is what the modulus. Next, what is the angle of this function? X of omega. A plus j omega it is given. Let's say simply if it is given a plus j omega. For that, what is the angle? Tan inverse omega by a. Because it is in the denominator, so the angle is nothing but minus. So minus tan inverse omega by a. So if I draw these functions, let's say magnitude spectrum, that is mod x of omega versus omega. Next, phase spectrum, which is angle of x of omega versus omega. Versus omega. Let's see. First, I want to draw magnitude spectrum. Omega value is equal to 0. Then this is nothing but 1 by a, maximum value. If omega increases, its values keep on decreasing. When omega reaches infinity, this value is going to be 0. In the similar way, if omega is negative also, the same value we are going to get. So finally, the spectrum, magnitude spectrum will look like this. This is what we are going to get. Whose value is equal to 1 by a. Now, what is the phase spectrum? If omega is equal to 0, its value is equal to 0. If omega is equal to infinity, its value is equal to minus 90 degrees. If omega is equal to minus infinity, this value is equal to plus 90 degrees. So, its value is ranging from, let's take plus 90 degrees. Next, minus 90 degrees. So if I take at minus infinity, its value is equal to minus 90 degrees and keep on decreases and again increases like this. So this is the function what we are going to get. So this is the magnitude spectrum and phase spectrum. If you observe carefully, magnitude spectrum, is it an even function of omega? Of course. If you fold it, you are going to get the same. So it is even. What about phase spectrum? Because for this one it is negative, so it is a odd spectrum. Odd spectrum. I already told you these things. Okay. Take it. Okay. Next, let's see the properties of Fourier transform. In that one property what I have to see is time reversal property. Time reversal property. What is time reversal property? Suppose if x of t signal having Fourier transform x of omega, then x of minus t signal having Fourier transform x of minus omega. So this is what the time reversal property. That means if you take minus sign for t, then you have to take a omega has to be replaced with a minus omega. That is the time reversal property. Next, we are having linearity property. Linearity property. What is the linearity property? Suppose two signals, one is x1 of t having Fourier transform x1 of omega, another signal x2 of t having Fourier transform x2 of omega, then ax1 of t plus bx2 of t having Fourier transform ax1 of omega plus bx2 of omega. This is the overall Fourier transform. That means if you add time domain, then we have to add the frequency domain also. That's what the meaning of it. Okay, take them. Then we will solve some questions based on this properties. Okay, listen here. What if I ask, what is the Fourier transform of, let's say, e power at u of minus t? E power at u of minus t. That means for here a is greater than 0. So let's see, check it out what it is going to be. First start from what we know. What we know? E power minus at u of t. This is what we know. Just now we have calculated the Fourier transform for this. 1 by a plus j omega. Then if I take t is equal to minus t, if t is replaced with minus t, e power at u of minus t. Then from the time reversal property, we have to replace omega with minus omega. Then definitely we are going to get a minus j omega. So this is the Fourier transform for e power at u of minus t. Let's see. Suppose if I take e power minus 2t u of t. What is the Fourier transform for this? 1 by 2 plus j omega. What if I take e power 2t u of t, u of t, u of t. It is not u of minus t, I have taken u of t. So many people will write like this, 1 by minus 2 plus j omega. If I say wrong, then the people will say 1 by 2 minus j omega, that is also wrong. Both are wrong. These are not correct. Why, sir? First of all, Fourier transform does not exist because it is a unbounded function. It is a unbounded function. I told you, for unbounded function, we cannot write the Fourier transform. So, Fourier transform does not exist. Does not exist. Next, what if I take a e power minus 2t, e power 2t u of minus t, then we can write 1 by 2 minus j omega. Why? This function looks like this one. Is it a bounded function? Yes, it is a bounded function. That's why we could write like this. But what about this function? This function looks like this. E power 2t u of t, which is unbounded function. For unbounded functions, we cannot write the Fourier transform. Okay. What if I take like this? E power minus 2t u of minus t. For this also, Fourier transform does not exist. Fourier transform does not exist. Why? Why it is not existing? See here, this is also unbounded function. It is a decaying exponential, but it is in the left side. So this is what the function it is going to be. So it is an unbounded function. For unbounded function, Fourier transform does not exist. So while we are writing the Fourier transform, please check whether it is a bounded or unbounded. Clear? Take this.